All right, everyone, thank you so much for joining us. I think 35 participants will be our magic number this morning. Thank you again for joining us as we talk about the science behind the uranium contamination in groundwater, specifically in wells. My name is Dr. Caitlin Hall. I'm an assistant professor at the University of Arizona. Joining me today is Wendy Miss, the Director of Health for the town of Glastonbury, Don Kendrick, the sanitarian, also at the town of Glastonbury, Dr. Rachel Coit. She was with Duke University and is now with the Ohio State University, and Dr. Hari Kandel at Lake Superior State University. So the team that we had going, we represented a bunch of different types of science, and we also had so many amazing leaders with the Glastonbury town staff, including Wendy and Don, but also Catherine Paquette, our amazing communications manager, really helped us get going, and as well as Richard Johnson, the town manager. Again, Rachel and Hari are the subject matter experts, and I am the Thriving Earth Exchange project facilitator. So before we get too much into the science, I wanted to chat a little bit about what this project has actually looked like. So, and also what Thriving Earth Exchange even is. So the town of Glastonbury contacted the Thriving Earth Exchange, which is with the American Geophysical Union. It is true to form. My internet kicked out, but luckily I noticed it. Okay, we're going to start over. So just to back up a little bit, hoping that I didn't lose folks too soon. Just want to talk a little bit about how this project started. So again, my name is Caitlin Hall. I'm with the Thriving Earth Exchange, which is a program in the American Geophysical Union, which is a consortium of over 120,000 geoscientists trying to understand what's happening with the planet and what's happening from science perspectives and how this matters for people in society. Thriving Earth Exchange is a volunteer organization where we connect scientists with communities in need of scientific expertise, like Glastonbury. So Richard Johnson, the town manager, and Wendy Miss contacted Thriving Earth Exchange saying, we see these amazing levels of uranium contamination in our groundwater. Why is this happening? What's going on? And Thriving Earth connected me into this project as a facilitator. We brought in Rachel and Hari as subject matter experts to understand why it's happening. Because what we were wondering is, where's this uranium coming from? What can we do about it? So we developed a project scope in fall of 2019, where we outlined, well, where is this coming from? Why is this happening? In 2020, we did some initial research. We gathered the water quality data and began looking at not only just the water quality data, but what was happening geographically and geologically, as well as why this might be happening from a chemical perspective as well. Why is this happening sometimes with one neighbor, but maybe not their another neighbor? But due to COVID, we had to pause because Wendy Miss is the director of health for the town, and naturally, she was very busy. So we took a pause. We restarted at the end of 2020, and we were able to connect with Wake County in North Carolina, who is also experiencing uranium contamination, to trade lessons learned and to understand maybe why this is happening, and as well as share information. With this information, as well as our gathered data sets from the amazing citizens of Glastonbury, we were able to draw connections to what was happening over a big picture of what's over the entire town, as well as what might be happening at the house level. We were able to complete our report, which is available online at glastonburyct.gov/uranium, which brings us to now. We did research, we started identifying what was happening, which we'll be going into, but now what? What are our next steps? And we're hoping that through this presentation, we talk a little bit about the technical aspects of our presentation or of our report, but also why it matters and what can citizens do now. So I just want to share that this is the data that we have so far from the town of Glastonbury, and this is available online, but I pulled it yesterday. And what we can see is throughout the entire town, we're seeing uranium levels higher than what the minimum or maximum contaminant level for the EPA is. And this is denoted by the larger circles as higher concentrations, medium circles, medium concentration, and the small beige ones are lower. So we were able to use this map and start connecting to the interesting geology, because we started realizing that the uranium contamination in the drinking water from wells was naturally occurring. It's not from an industry. It's just, this is something that is natural. And we were able to start to understand why, and seeing the complexities as to why one neighbor might be experiencing high uranium and others might not. But I'm going to pass it over to Dr. Hari Kandel to talk a little bit more about what this actually means.
Hello, everyone. I'm Hari Kandel. I'm an assistant professor in the School of Natural Resource and Environment at Lake Superior State University. As Dr. Hall mentioned, I was invited as a geology expert for this project, and we asked the question why we have uranium in certain wells higher than the other wells, and if it related to some geologic rock units or structure in there. So at the beginning, we started with the statewide geologic map that's shown on this slide here. As you can see, the color-coded geologic units and the lines that are passing southwest to northeast in the middle of the map. These are the fault lines we're talking about. They are the geologic discontinuity of the movement of the rocks. What that does is it throws some of the rock units upwards and the other units downwards based on how the orientation of the fault plane is located at that particular region. And what we are looking at here is towards the east of that fault line is the geologic unit, the rock unit called Glastonbury gneiss. This is the metamorphic rock. When I say metamorphic, it is the changed or deformed rock from the original igneous rock, which was deposited around like 460 to 470 million years ago. And then the metamorphosis happened in the Devonian age, which is about 420 to 300 or 380 million years ago. So towards the west part of that the fault plane, you see this the orange yellow colored rock unit, which is completely different, and partly the sedimentary rock unit. So we have two contrasting rock units. And can you go to this next slide, please? We wanted to see what mineral types we have in the Glastonbury, especially Glastonbury, because you'll see in the next slide that this is the rock unit we have the higher concentration of uranium. So as you can see on this slide, this is the microscopic image of the very thin section of the rock. The special mineral focus here are the magnetic titanite and the metamorphic titanite. These are the minerals studied before and reported as containing the uranium in the inclusion or substitution. That means that in the molecular structure, the original elements or original ions will be replaced by some of the uranium ions. Similarly, the other minerals, like we have biotite, these are the platy minerals, epidote, amphibole, plagioclase, quartz. Some of these minerals may have uranium containing it as inclusion or substitution, or as served into the surface of the mineral. Can you go to the next slide, please? So as you can see on this one, this is the the data we pulled from the Department of Environmental Protection of the Connecticut. The background map is the geology, as you saw before. That's the same map, statewide map. Now it's only for the Glastonbury town. We have the orange color unit, majority of the area covered by that, the granitic gneiss. And again, towards the closer to the fault, towards the west from that orange color unit is the schist. These both rock types, the gneiss and the schist, are the metamorphic rock, almost containing the same mineral composition, but different grade of metamorphism. As you can see, most of our, almost all of our higher concentration uranium, the uranium are plotted as the cross sign is less than 30 ppb, which is, we're talking about 30, let's say 30 liter of uranium in billion liter of water, which is the EPA's maximum contaminant level. And then with the circle in the central dot are the 30 to 900 ppb, which are above the maximum contaminant level. And then we have a few samples that are higher than 900 ppb, which were close to about 4,000 ppb as well. So all of these sample, the water sample that have the higher concentration of uranium are overlying on this Glastonbury gneiss unit and a few onto the schist, the Colleen Hills Formation, that's what they say, the schist rock. The link on the left, bottom left here, can be used to access the bedrock geology. This is the interactive GIS map prepared by the Department of Environmental Protection. So everyone can access that and see what rock type we have around the area you are living. Next slide, please. So then comes the Quaternary geology, which is about 70,000 to 100,000 years ago. What happened is the glacial action in that time eroded the rock, which the crystalline rock or the sedimentary rock that were exposed on the surface. And then those eroded rocks were broken down and deposited as the glacial deposit, which we have on the surface of the Glastonbury. Can you go to the next slide, please? The process of the glacial deposition, the glacier itself erodes and deposits, and when the glacier starts to melt down and it becomes water, then the glacier and fluvial mixture, the water and the ice mixture will carry the sediment down and deposit. So when it does that, whether it is glacier or glacial-fluvial mixture, it mixes all different kinds of sediment together. The fine sediments like silt, clay, and sand to coarse sediment, pebble, cobble, and boulder-side sediment will be mixed together. That's what the name we have is till, the common till. And the next slide, you'll see that common mixture of those. So this is the Connecticut River we're looking at on the left map here towards the west side. And mainly we are looking at the units that are overlapping with the higher concentration of uranium. So these are the thin till and thick till. So the thin till are basically about 15 feet thick surficial sediment on the close to the surface, and the thick till are the maximum thickness of that till is about 30 feet, and these are the lower till. Sometimes the thin till stays on the top and the thick till on the bottom. Sometimes the thick till itself exposes into the surface. But if you look at the map on the right, that has the uranium plotted together, majority of the high concentration uranium are plotted on this unit called thin till. So the thin till, which is thinner, that means the surface water can easily percolate down to the crystalline aquifer, the granitic rock, the gneiss rock. and that can easily extend the surficial water and the groundwater. So that's where we see the higher concentration of uranium in here. And we wanted to know why that is the case, and that Dr. Coit will be talking about that, but it's mostly the interaction between the surface water and groundwater. Can you go to the next slide, please? And so at the conclusion of that geologic study, we have the bedrock aquifer, which is mostly the fractures and faults and those interconnected openings. That's where the water sits in and covered by the sediment, mixed sediment, which is till. And in the thin till area, we have the very enhanced interaction with the surface water, and that's where we see the Glastonbury gneiss is the one that has the uranium containing mineral, uranium bearing minerals, and the wells that have higher concentration of uranium are mostly lying under the thin till. Means that the interaction with the surface water has something to do for the uranium concentration. So I think I complete with that, and we have some questions that I'll answer later.
Thanks so much, Hari. Before we pass it on to Rachel, I was remiss to say, I mentioned it in the chat, but if anybody has any questions that they weren't able to submit prior to this presentation, or that come during this presentation, feel free to put them in the chat. I will answer them as I can, but if it requires a more intensive response, we'll be putting together some resources that we will be posting online with updated information and as well as answers to your questions. Thank you so much, Hari. And I'm going to pass it on to Rachel to talk a little bit about the water chemistry.
All right. Thank you, Hari and Caitlin. My name is Dr. Rachel Coit, and I am a geochemist. So I study really what are the drivers of water chemistry, and in particular, how water-rock interactions lead to what we see in water chemistry. Whereas Hari covered a lot of the background geology, I'm going to talk about what the connection is between that background geology and what we're seeing, and in particular, why there's so much heterogeneity. When we looked at those slides that Hari posted, most of our samples were taken in what is ostensibly the same bedrock geology, the Glastonbury gneiss. However, what we see when we're looking at that map is that we can have samples that have extremely high concentrations of uranium, higher than 900 parts per billion, next to wells with very little uranium, less than 30 parts per billion. So what's really driving this heterogeneity, and why can wells look very different despite being in close proximity? Next slide. So I'm going to back up a little bit and talk from a broader view about what sort of things drive groundwater quality, and in particular, groundwater quality with respect to uranium concentrations. One of the first things that we think about when we think about groundwater quality is local climate and recharge. So in very dry environments, we're more likely to find high concentrations of uranium. But we also can see that some areas have seasonal trends, depending on what type of recharge and precipitation they can get seasonally. And we'll talk about that a little bit later on as it applies to Glastonbury. We can also see in certain areas that influence from the surface activities. So things like mining, certain industrial sources can lead to groundwater becoming contaminated. In the case of Glastonbury, because of the diffuse nature of the contamination, or of the uranium concentrations, the elevated uranium concentrations, and the lack of an obvious source that would create such a diffuse amount of elevated uranium, it's unlikely that this is a big driver within the Glastonbury context. We also have age of groundwater. So the amount of time that groundwater spends underground before being pumped up to be consumed can also affect the amount of uranium that is in there. If groundwater spends a lot of time in interaction with rocks that have high concentrations of uranium, it might have more time to leach that uranium out and thus produce higher concentrations within the groundwater. And then finally, when we look at the literature and we look at fractured rock aquifers in very humid environments, like the case of Glastonbury, what we really see is that geology is the big driving force behind groundwater concentrations of uranium. You have certain geologies that tend to produce these high concentrations of uranium. So with the Glastonbury context, we've got that geology background from Hari, but why is it that even in the same geology, we're getting different concentrations? And one of the big things I want to draw your attention to is the fact that geology is heterogeneous. Next slide, please. This is a granite countertop, something that many of you might be familiar with through seeing in restaurants, perhaps even your own home. And when we look at this big slab of granite, a rock that's very similar to what underlies Glastonbury, one of the first things that you might notice is that we have a great diversity of colors and textures. You have some areas that have this brilliant white, some areas with smaller pockets of white and streaks through it, yellows, browns, greens. This difference in texture and color represents a difference in chemistry in many cases. Next slide, please. To bring it a little bit closer to home, we can look at some rocks from the Glastonbury area. These are from the Wesleyan University Natural History Museum, and these are all rocks that were collected around the Glastonbury area. Glastonbury used to be a very prized location for rock hunters because of certain types of fairly rare minerals that could be found in the area, especially in abandoned pegmatite mines. And with these rock samples, we can see a good deal of heterogeneity, even in rocks collected in the same unit in similar locations. We have different colors, different textures, different types of crystals. In particular, with these samples, we have a green mineral in the middle that is actually a fairly rare high uranium mineral that we see in this one rock sample, but not in any of the others collected from a similar area. Next slide. In addition to having certain types of chemical heterogeneity, we also have physical heterogeneity. So as Hari mentioned, a lot of wells in Glastonbury are actually drilled into the fractured bedrock. These fractures don't all necessarily form a nice predictable network. It can be a very complicated underground network, so that wells that are drilled very close to each other may be getting water from very different fracture networks, very different places, despite their close proximity. Next slide. We also see some evidence that there are water level impacts on uranium concentrations. We have a few examples in our data set of wells that were tested at different times of the year when water levels are different. There's this very predictable seasonal fluctuation to groundwater tables in the Northeast. So looking at the data, we see that sometimes there are very different concentrations depending on if you test in the spring or the fall. What we think is happening here is that as water tables fluctuate, different fractures are contributing different amounts of water to the aquifer itself, to what is coming out in the well. And these fractures may have higher or lower levels of uranium. The data we have, we can't predict whether or not uranium concentrations are more likely to be high in the spring or high in the fall in an individual area. It depends on the well itself, but we do know that these fluctuations can happen. Next slide, please. And then finally, we also see that deeper wells often have higher uranium concentrations. We found this throughout the study area. And while we don't know exactly why, and we can't know without further study, we have a few possible reasons that this could be. It could be a feature of the geology. It could be that the deeper you go, you have different amounts of uranium, average uranium concentrations within the aquifer. It could also have something to do with residence time, like I mentioned previously, the amount of time that water spends in an aquifer. If it spends more time in the aquifer, as could be the case for some deeper water, that could mean that you have higher concentrations of uranium ultimately. Next slide. So to kind of give a summary of this section here, we see that spatial heterogeneity is quite high throughout Glastonbury. a lot of this is due to the fact that the geology is quite heterogeneous, despite all being part of the same formation. Uranium concentrations can change seasonally. So just because you have one test for uranium concentrations, that doesn't mean that your test is going to look the exact same in a different season and under different conditions. And then finally, we know that deeper wells usually have higher uranium levels in Glastonbury. So I'm going to change gears a little bit and start to answer another question, which many of you have posed, which is, what does this mean for human health? Next slide, please. So there are a few things that we know for sure when it comes to uranium and human health. The first is that your risks related to uranium ingestion are related to concentration, so the amount of uranium that you're ingesting, the mode of exposure. So in this case, with drinking water, we're interested in ingestion, but dermal exposure or inhalation have a different set of effects than ingestion do. And then finally, the duration of the exposure. So are you consuming 2 liters of water for 70 years, or is it a weekend's worth of exposure? Past that, things get a little bit less clear. We have recommendations from the EPA and the World Health Organization of 30 micrograms per liter for a limit of consumption. This is based on possible effects for kidney health, but there are other biological effects that have been pointed to in the literature that are a little less clear, and particularly those mechanisms of action and why the uranium is harming the body are less clear. This is partially because controlled studies of humans are unethical, so this can be really difficult research to do. We have to rely on animal models, cellular models, as well as epidemiological information, but there has been a lot more interest in this type of research in the last few years. A lot of this is because people are realizing that uranium exposure through drinking water is much more common than we previously thought. So I'd say this is a space to watch for more studies coming out in the next few years. Next slide, please. There is a very good review that was published in 2020, which we cite in our publication. We also are in our report that's on the website. You can also see a summary of the literature in our report on the website. But a few things to highlight from this infographic are, one, the nephrotoxicity, so effects to the kidneys. There is some decent evidence of kidney toxicity from ingesting uranium high drinking water. There's also some decent studies out more recently, particularly epidemiologically based studies that have seen reproductive health effects. But again, I would point you to this study in particular, as well as our reference section in the report, if you'd like to know more about this. And with that, I think we're moving on to Caitlin.
Thank you so much, Rachel. Okay, so I think also I really want to emphasize that uranium contamination that's impacting Glastonbury's well water it's naturally occurring. So I want to really emphasize that it's no one's fault. So the reason that we started connecting with Wake County in North Carolina was because we wanted to talk to somebody who was also experiencing something that was naturally occurring. Whereas I think when I think about uranium contamination, I think about like the science fiction movies, and it's like, oh, someone's poisoning our water, but it's not. And it's really complicated because the geology really matters, how deep your well can impact it, what aquifer you're pulling from. So that's why when we started this study, Hari looked at this from a large scale. So he did all of our GIS work. So what that means is looking at how the geology and the geography influence uranium occurrence in well water. And then we took that information and Rachel synthesized it to see like, okay, well, why are these things happening? And she was able to look at trends to start understanding why someone might see a level greater than 900 or 30, depending on seasonality. So we were able to come together and see what I kind of call the engineer's way out for an answer is when someone asks, well, am I impacted? It's like, well, it depends. And that's kind of a cop-out answer when I've gotten it. I'm never happy about it. But Advice that I would give to all citizens that are using private well water not on public utility is, when they ask me, should I test my well water? Yes, the answer is yes. Your neighbor's tests do not mean yours, because as both Rachel and Hari have mentioned, that you might be pulling from different aquifers. There's so much heterogeneity, which means differences in the geology, that your results might not look like your neighbor's results. And then how to do this is also outlined online at the glastonburyct.gov/uranium. And they have a list of vetted companies at the end of the page. So if you scroll down, there's like an expansion, and it says water testing companies, and it's there. So go there, but make sure that you're looking at the specific sample protocol for each company. And Tony Patalunas, I see your question. We will be getting to that shortly. It's looking at suggestions about seasonality. Now, I'm going to pretend I'm a Glastonbury citizen who has found that uranium greater than 30 ppb is in my well water. Now, what do I do? Go to our handy dandy website. That's going to be my, if you leave this presentation with nothing else, just this website is where all of this information is, and this is where all guidance is, including who to talk to. But we need to, it would be amazing if you could report your results, because this is helping us not only from a research perspective of understanding why this is happening, but this is powerful information that town leadership can use to help advocate for its citizens in terms of treatment, remediation, or other opportunities to protect public health and ensure safe drinking water. Then, so if you found uranium, call your water treatment company to start identifying options, which we'll be going into shortly. And if you have any questions, call the Glastonbury Health Department at this number below to walk through different treatment options that fit your needs. The two water treatment options that we explore are reverse osmosis and anion exchange. So reverse osmosis is relatively low initial cost. Upkeep requires some cost, because how this works is you have untreated water that gets passed through filters that essentially filters your water such that then what comes out is very purified. But because this uses a filter, you have to change out that filter, so upkeep can get expensive. Now, reverse osmosis, or RO, is more point of use. So you're thinking like, okay, I want to make sure that I'm not showering in this and water that might have uranium levels. I'm not drinking it, things like that. Whereas when we want to scale up to a whole house, so like my laundry isn't connected, my XYZ isn't connected, you want to look at anion exchange, but that's a little bit more expensive for its initial cost, but its upkeep is lower. And how anion exchange works is you have the untreated water that goes through, and as Hari was mentioning and Rachel expanded on, due to different chemical reactions, they're able to kind of bind the uranium through different treatment processes, so that what comes out doesn't have uranium. But anion exchange, while it's a little bit more comprehensive because it's your entire house, you have waste that comes from it. So you have to look at waste permitting and making sure that it's being disposed of properly. But right now, we recognize that those treatment options kind of feel like Band-Aids, but they are the best options right now, because we can see that there's no at-home treatment that cannot be treated with those at-home options. But what about looking forward? What about the long term? So Glastonbury is currently exploring options. They're working to extend public water service with Tie and Bond. It's an engineering consultancy in the area, because they're looking at, is remediation the best option, as well as extending public water service. So remediation, what that means is underground or below ground treatment to try and remove the uranium from the groundwater. But as we've talked about, because the geology is so complicated. The aquifers aren't connected. Remediation can get tricky, but we're trying to figure out, or the town is trying to figure out what the best option is. And not only that, but making sure that the cost to citizens is alleviated. And current legislation is pending federally to try and ensure clean water access. Additionally, Connecticut state is looking at, or the state of Connecticut is looking at opportunities to do large-scale testing for the state, which can really help showcase why this is so needed to try and get different funding options to best support citizens in their public health. Now, going forward, again, if you take home anything, it's that the website listed here that the town leadership has put together has the most up-to-date information on treatment and where the town is at in terms of its actions. You can find guidance on who to contact for questions, how to sample your water, and what to do if you have uranium in your well water. Thank you so much for joining. That was our summary about our findings. If you have any additional questions, please put them in the chat. But if maybe you're on a walk later and something else comes up, please feel free to forward your questions. Just head to that website and we'll do our best to answer them. I wanted to highlight again our amazing team from the Glastonbury town, with Richard Johnson, the town manager, Wendy Miss, the director of public health, Don Kendrick, our sanitation engineer, and Catherine Paquette, communications manager. And before anyone hops off, we have a lot of questions that we'll be going through that were posed. So don't get too excited. We're not done yet. And I also really want to thank Dr. Rachel Coit and Dr. Hari Kondel. Again, my name is Caitlin Hall, but I just want to emphasize that the scientists are doing this pro bono. So they are volunteering their time to try and help protect Glastonbury's public health and understand why these things are happening. So from my perspective as the project facilitator, I am just so grateful that we had such an amazing team that worked so well together, and we're able to create some real product that's helping advocate for the citizens of Glastonbury. So this project and this report is being used to advocate for for legislation as to why this is really important and why we need assistance from the government from federal funding, as well as identifying different treatment options to make sure that we're protecting the most people as well. So now on to the time that we've all been waiting for, questions from the community. So Hari, question to you, what rocks and minerals in Glastonbury contain uranium?
Thank you, Karen. So as I talked before about the geology of the Glastonbury gneiss, the gneiss is the metamorphic rock. And it is a metamorphosed from the original igneous rock called granite. And that is considered the felsic light-colored igneous rock, which is deposited into the subsurface. And then during the depositional process, and depending on the source of magma, we have different types of the minerals deposited. So generally studied from Glastonbury gneiss and studied elsewhere that have shown the connections of uranium bearing minerals with the granite and gneiss, shows that the titanite, which can be there in the potassium feldspar, which is the flesh-colored mineral in granite or gneiss sample. It can contain the K-feldspar crystals, can contain the titanite, and that can have substitute uranium as a substitution. Uraninite, another mineral that can be there in the pegmatite, the very coarse grain rocks, the igneous rocks, and the veins in the rock sample. So these are the two minerals we think are present in those gneiss, the Glastonbury gneiss too. The other minerals that are reported in the literatures are monazite that can contain the uranium oxide, which is uraninite, as the solid solution. Means again that you may not see the uranium rich mineral, but that mineral can contain the uranium as well. Zircon, apatite, allanite are some other minerals that can contain mineral. So again, the process here is, first of all, the uranium containing minerals, some of these minerals are deposited in the granitic rock. And after 50 or 60 million years, they were metamorphosed. And during the metamorphosis, metamorphosis is the change from original rock to the new rock, which is the structural change, the form of the rock starts changing, the minerals are recrystallized. During that process, the concentration can change from the original rock to the new rock. And it's not just that. After that, we have the glacial process, and some of the exposed rocks are weathered because of the air and the water effect, atmospheric effect. And during that process, the original minerals may have changed, dissolved into the water, and got into its waterways. And again, we are talking about the crystalline rock aquifer, and that aquifer, the water comes from the fractures. So the water is not uniformly distributed. That's why some of these minerals may be in higher concentration or higher frequency occurrence in some of those veins, and the other sites you may not see that kind of concentration. That's why they spatially heterogeneous. And we also asked about why within the Glastonbury gneiss also, why only the higher concentration are concentrated towards the fault line that we saw in the middle of the Glastonbury town. We think that the orientation of the rock towards that fault plane, I mean, the rocks are dipping towards that fault plane, means the water flows towards that fault plane, and the fault plane itself creates more conductive zone for the water to dissolve and have the longer interaction with the mineral. So that's why it's not just you pick a rock sample, a mineral sample from the Glastonbury gneiss and find a particular mineral. So I got this mineral here, means we have higher concentration. There is a complex process of hydraulic conductivity, mineral dissolution, and the reactivation of some of the minerals with time. That's what is affecting the higher concentration, we believe. Thank you.
All right, Hari. So could you just elaborate a little bit more on why some wells have different water levels as well, and why this changes over time?
Sure, thank you. So as a hydrogeologist, what I can say about the crystalline rock or the fractured rock aquifer is whether these are fractured rock or with the unconsolidated, I mean the sandy or gravelly aquifer. First of all, the water table tend to mimic. So whatever the elevations of the surface are, water table will be higher. If the surfaces are higher elevation, the water table also will be higher in those areas, and the surfaces at lower elevation, for example, the wetlands or depressions or streams, the water will be following that topography. So that is the natural occurrence of water table. But if you overpump, for example, we have a very small mound, and that particular small mound, that hill has number of wells pumping the water, and we don't have enough recharge through the precipitation or snow melt. In those seasons, we are extracting more water than we are putting water into the aquifer. That's why the water table may fluctuate in those areas. And the flow and the level of well also depends on because these are the fractured rock, hydraulic conductivity, which is how much of those fractures, what is the density of the fractures, how bigger, how larger the fractures are, and what is the orientation and connectivity of the fractures together. So if we have very high hydraulic conductivity and high hydraulic gradient, which means the source region to your well is close, and there is a high elevation difference between the water table and your water well, then the water flows easily. The other slide I have here, can you go to the last slide, please? Is showing the influence of neighboring wells. As we draw the water nearby the well, you can see the cone of depression forming. I mean, the very low water level close to the well compared to the surrounding region. And if we have neighboring wells pumping the water out, then the combined influence will be basically lowering the water table in that region. So that may be the reason why the particular well can see the water drying out, or will need to go to the deeper layers to get the water when there are neighboring wells pumping the water out. Thank you. And if we have any more questions, I'll be happy to answer those.
Thank you. So I'm going to pass the conversation on over to Rachel, but just want to open this to the team. If you have anything else that you want to add on for those questions, feel free to interrupt me. Just throwing that out there. That goes for everybody on the team. So Rachel, should I test my well at different times of the year?
Yes, it is a good idea to test your well. We recommend in spring and fall because those tend to be the extreme points of high water table versus a low water table. To be safe, that's because, as we said before, we have seen cases where we have pretty big seasonal differences. This was one well for which we had multiple observations. We had 3 observations in the fall and 3 observations in the spring. The fall observations had uranium concentrations on the order of 105 micrograms per liter, whereas the spring observations had concentrations on the order of 4,000. So this is a very, very large difference.
And could you recontextualize? It's 30 micrograms per liter is the EPA maximum level, right?
Correct. So in this particular well context, all of the observations were over the MCL, but there could potentially be another well which has a different spread. And so just to be safe, you want to have a better idea of what the full range of uranium coming out of your well water is.
Awesome. Thank you. And also thank you for taking an unprepped question from me.
No problem.
Okay. So another question that was posed was, how do I find information about a specific home or area? So due to privacy reasons, we have no house-specific data. So any information that folks submit, so let's say I am Caitlin at 1001 Mabel, and I see that's my work address. So if it's an actual house, this is not related. And I submit that information. I'm submitting that knowing that all of this information will remain confidential. All of the information that we have presented here today on this map is doesn't have any streets connected to it, so that no houses are like, oh, that is Caitlin's house is the one that has it. We do that for privacy reasons because it's not ethical to share that information, but what we can see here are the more impacted neighborhoods and areas, which is helpful for us to understand location as to where things are happening and who should be testing their wells. The maps that you've seen here are compiled of the information that we've gotten from individuals, but even though we have seen it, the information that even we have processed, even after agreeing to confidentiality, doesn't have addresses. It's been anonymized. Another question was, what is the town's plan for building sites within the areas impacted? So the town doesn't build private sites. So there's no, the specific question was asking about residences that the town might build. The town doesn't look at that. However, land development requires regulatory review, and each house and building must have access to potable water or potable water. So what that means is you have, since May 2019, all new wells must be tested for uranium and radon before they're approved. So if a new area is going to be on well water, there has to be well water testing done before any building can be opened. But just trying to clarify that it's we're not saying don't develop here. We're saying that there are regulations that one has to follow to make sure that people are staying safe. Another question was, so should we do well water or expand public access? And other questions from this were which treatment is better, so RO or anion exchange? And I'll answer that one first. Each house is going to be different. The cost is going to vary. So the reason that we don't put any amount up here is because the house specific costs will vary. So you need to work with a designated water treatment company to see what is going to be best for your particular situation. Now, looking at, do we stick with at-home treatment options or public water utility? The benefits of sticking with private well water is that, yeah, of course, it's less expensive, but then the onus of cost is likely going to be on the homeowner rather than being able to work with federal or other potential funding opportunities like federal or state. Residences are already set up for well water, so that's a benefit, but they're also going to more likely be impacted by groundwater contamination and also water scarcity and water levels due to changes. So that's where we advocate for public water utility, because there's just much lower risk of water scarcity and contamination. There's nothing, until you have some sort of treatment, there's no promise that yes, you will or will never experience uranium in your groundwater. So these are just things that we don't know the answers to and will not be able to predict as well either. We do recognize that public water utility is more expensive and it requires infrastructure. So that's why we advocate for at-home water treatment until long-term plans can be determined. And again, what water treatments exist now are reverse osmosis or RO or anion exchange. And we recommend that folks invest in those and work with the company to determine the best fit technology for them. Another question was, are there existing medical checks for long-term exposure to high uranium levels? To our knowledge, there's not. A specific panel, like I wouldn't be able to go into my general physician and say I want the uranium health panel check, but there are likely tests that can be run. It just doesn't have a name, so to speak. So our suggestion is to talk to your doctor or call the Connecticut State Department of Health for more guidance and more information on that. And the age-old question of when will access to public utility water happen? So the town of Glastonbury initially started looking at the cost for what it would take to expand to public water, expand the public water utility, and they were very costly. So what town leadership is trying to do now is identify different grant and funding opportunities through federal and state legislation to alleviate the cost to homeowners and citizens. Since we're waiting for information on what opportunities are there, there's a little bit of a holding pattern, but town leadership is working right now to try and to advocate for Glastonbury citizens and to find the best option and solution to this issue. All updates will be announced publicly on our website. How is the town trying to alleviate costs? As mentioned, the town is currently exploring options for different funding opportunities to reduce costs to citizens, to primarily expand public water utility access or to aid in remediation. But as we've talked about, remediation can be complicated and costly, whereas public water utility access is a more permanent solution because we aren't at the whim of nature. But more information on this is in the works and will be made public as soon as possible. And that leads us to the end of our presentation. I just wanted to say thank you again for joining. And also, if you have any follow-up questions about actions that the town will be taking, please pose those to the website. But the purpose of what we were trying to do here is, again, understand what's happening from a science perspective and a public health perspective as well. So I wanted to thank our volunteer scientists, again, Dr. Rachel Coit and Dr. Hari Kandel, as well as our excellent team members from the Glastonbury town staff. Again, this was totally done from volunteer time from our scientists and from the members of Thriving Earth Exchange. So we're very grateful for their time. And the more specific questions about actions is best posed to the folks at Glastonbury. We can't answer those as easily. I am writing down all of the questions, and so I believe is Wendy, to make sure that we are holding on to the questions that you all asked, such that if we were not able to get to them today, we will answer them in more detail on the website. And again, if you have any other questions that you want to pose to the team after this presentation, as you're thinking about it, please reach out via our website. I want to pass it on over to the team. Do you have anything else that you all would like to add? Okay, well, thank you everyone very much for joining, and we look forward to working with Glastonbury more.
Thank you, Kathleen and the Glastonbury team for leading this project. The team has provided us enough data to understand the process, and that was helpful to understand the natural process here, uranium contamination and the geologic connection to that. Thank you very much. Thank you all for your attendance here today.
Yes, thank you to all the attendees and all team members.
Wonderful. Well, I'm going to pass it to Wendy for the final end meeting, or not.
Sure. Thank you to all the Thriving Earth Exchange scientists. Your work is greatly appreciated. It's been a pleasure to work with you. This has been a tremendous presentation, and we hope to connect again. Thank you so much, and ready to close the meeting.
Wonderful. Thank you.